So welcome everybody to today's imaging seminar. And my name is Eric Bontier. I'm the host of today's seminar, and I'm very happy to introduce Faouzi Triki, one of my colleagues from Grenoble. Faouzi, colleagues, friend, and collaborator, I should say. Faouzi obtained his PhD in 2002 at École Polytechnique. And after a couple of years at Michigan State University, got a position as maître de conférence at the University of Grenoble. And he's an expert in PDEs, control theory, inverse problems, imaging, and particularly he's been interested over the last years on he's been interested in inverse problems with internal data. And I think today's talk is about this topic, as it is entitled Hölder Stability of Quantitative Photoacoustic Tomography Based on Partial Data. Faouzi, the floor is yours, but just a word before concerning questions and comments. Feel free to use the Q&A box or the chat box to put your questions, and then we'll unmute you either at the moment or at the end of the talk to take your questions. Faouzi, please, whenever you want.
Thank you, Eric, for the invitation, for your nice presentation. I'm very glad to be here and to present my recent work on photoacoustic. I know that you had already two nice talks about photoacoustic by Otmar and Simon. So the presented result are obtained in joint work with Eric, with Mourad Chouli from Metz University, Quiren, Taoyin, and Qi Zhu, postdoc in Grenoble. So let me remind you what we mean by photoacoustic effect and photoacoustic imaging, the whole concept. So it started in 1880 by Bell. So the idea is to, can we hear the light or see the sound? So can we have a converter that convert the wave, the electromagnetic wave to acoustic wave, or from the acoustic wave to electromagnetic wave? So the idea is very simple, and here we will use the mouse as a converter. So we send the laser on the mouse, electromagnetic wave. The wave will hit the absorber because the electromagnetic energy is absorbed by the biological tissue of the mouse, and when the biological tissue absorbs the light, the electromagnetic energy, it will expand and generate an acoustic wave. So the acoustic wave will propagate toward the detectors, and we will measure the acoustic wave. We register the acoustic wave real time. And the question, can we take advantage of the coupling between the two waves in order to improve the image of the biological tissue? So this is the concept. So we need, in order to take advantage of this coupling, we need a mathematical model. So this is mathematical model for the photoacoustic effect. And so in the diffusive regime, so the electromagnetic wave U satisfies this elliptic equation. Here dA and mu A are the optical coefficient, the target optical coefficient that we want to recover later. So dA is, here we consider it a strictly positive function, mu A is strictly positive function, and we assume that we are in Rn, the whole space. So the S is the source of the electromagnetic wave. It is outside the mouse. The mouse here will be represented by the domain omega. Of course, we assume that the electromagnetic wave will decay at infinity. And this electromagnetic wave will generate an acoustic wave. And the acoustic wave, acoustic pressure, P satisfies this wave equation. So C is the speed of the wave. So here we assume that we are in the bounded domain omega. Omega is the space occupied by the mouse. And we assume that the initial pressure at t equals to 0 is exactly the absorption energy, is the absorption coefficient mu a times u. U is the fluence of the laser. Okay. And we also assume that the speed of the acoustic pressure at t equals to 0 is 0. So here we considered the wave, the pressure wave in the domain omega. So we added this attenuation on the boundary related to the transducer. We'll talk about this later. And you can see the coupling is through this term, this red term, mu a times u again. Okay, so we measure the acoustic wave on the boundary of omega for an interval of time, 0 capital T. And here we consider the optical coefficient dA and mu a. dA is the diffusion, mu a is the absorption, constant outside the domain omega. So this is the mathematical model. Now we move to the inversion. The inversion, what we want to recover. So we measure the acoustic wave on the boundary again for an interval of time. What we want to recover are the three coefficients: dA, mu a, and c. So dA the diffusion coefficient, mu a the absorption, and c the speed of the acoustic wave. So we have two steps. The first step is the acoustic conversion. So we use the acoustic measurement on the boundary to recover the speed of the wave and the acoustic the initial state, the pressure at t equals to 0 in domain omega. So we use this model, I mean the wave equation, the same model, to recover at the same time, as I said, the speed and the acoustic pressure at equals to 0. Once we did that, we moved to the optical inversion. The optical inversion is we assume that we have the initial pressure at equals to 0, mu a times u, and we want to recover both coefficient, dA and mu a, through this diffusion equation, this elliptic equation. Of course, here we know the source. The source is, we assume that the source is compactly supported outside omega. So here will be 0 inside of omega. So this is the model for the inversion. This is the big picture. So in one way we have the direct problem, and the other way we have the inverse problem. Okay, now we have few observation related to the experiment that have been done on this imaging modality. So in practice, the people assume that the speed is constant. This is the first observation. The second observation is the physicists only perform the first step, the acoustic inversion. They will never do the second step. And the third observation is that the resolution is very limited in depth. We will see why. So let me first talk about some physical hints related to these three observations. So the first observation, why we assume that the speed is constant, is because the biological tissue is approximately 80% of water. So this is why we assume that the speed is almost constant. And why we don't perform the second step, we just stop at the first step, is because when we solve the first inversion, we recover the initial pressure at equals to 0, and we got this image, and you can see this image is a very nice image, contrasted image. And we just the people are happy with this image, and they stop there. They don't perform the second inversion. They don't want to recover the optical coefficient dA and mu a. And the third observation is why we have a very limited depth resolution, is because the photoacoustic signal is very weak. Okay, let me now talk about, mathematical explanation of these three observations. The first is when we assume that the speed is constant. This will simplify a lot the first inversion. You can see. Let me go back to the first inversion. You see, this is the first inversion. So if you assume that the speed is constant, so you don't have to recover the speed at the initial pressure at the same time, which is an ill-posed inverse problem. So if you assume that the speed is constant or is known function, the problem becomes linear, since we want only to recover the initial state, and the problem becomes more classical. And let me briefly explain what the people do in real life. To solve this inverse problem. So we assume that we know the measurement of the acoustic wave on the boundary. So we register the wave on the boundary for an interval of time between 0 and capital T. So we assign the initial state Px at t equals to 0, the boundary measurement Px and t on the boundary for t between 0 and capital T. This is a linear operator, linear bounded operator in the energy space. And we use this measurement of the acoustic wave on the boundary to reverse the wave from capital T, and actually we solve this wave equation of the same speed, but at capital T we assume that the solution V is exactly phi capital T, with phi capital T is the solution of this, is harmonic inside omega, and it takes the pressure value at capital T on the boundary. And we assume that the speed is 0, okay? It's like an improved version of the reversal time method, classical reversal method. So if we assign this boundary measurement, the initial, the solution V of this problem at t equals to 0, then if the wave is these conditions at capital T are exact, we expect to have V exactly with V coincide exactly with the initial pressure. Okay, but in real life, you know that this is an approximation, and we'll see that actually if we apply A to the operator lambda, we will obtain actually a Fredholm equation, C density minus a compact operator. Of course, here you need some geometrical assumption, otherwise it won't work. And the geometrical assumption here is that the metric is not trapping. So Ullmann and Stefanov proved that actually if you apply A to lambda, you get identity minus K, with K is a compact operator, and actually with norm, energy norm is strictly less than 1. So we can solve this you can invert the operator lambda using Newman series. So this is what the people do in general, when the speed is known. Now I move to the second observation, is why the physicists stop at the first inversion. They will not perform the second inversion, and this is because if you see the image, you have a very good contrast, and you can see here the blood vessels very well. And why? Because if you the initial pressure, if you see the initial pressure. The initial pressure exactly the product of the absorption coefficient, which is here piecewise constant, the piecewise constant coefficient, the absorption. This is what we see, the absorption coefficient times u. U is the solution of the elliptic equation. If you can go back to the second inversion here, you can see. This is u, the solution of the elliptic equation, and S, as I said, is compactly supported. So we have 0 here in omega, So U is a solution of an elliptic equation, and if you assume that dA and mu A are piecewise constant coefficient, you can apply the Giorgi result related to elliptic regularity, and you deduce that U is actually Hölder continuous with Hölder power that depends on the jump of dA and mu A. So basically here you have, if you recover the initial pressure, you have the product of piecewise constant function by a Hölder continuous function. So this means that the discontinuity of the initial pressure is exactly the discontinuity of the coefficient mu A. Okay, and this is why in the image of the initial pressure we can see clearly the discontinuity of the absorption coefficient, and the people get excited about these results. And here I just made a numerical example. If you assume that mu A and dA are piecewise constant with very weak, not very strong contrast here, and consider this boundary measurement, you solve this elliptic equation. This is the map of U. You can see U is smooth, and you cannot distinguish the discontinuity of the inclusion. Sorry. You cannot see the discontinuity of the inclusion, in the map of U. But if you multiply U by mu A, you can see it clearly, and you can see it. You see the discontinuity of mu A in the product. This if you don't care about the source, you don't care about the model, and you get this image, and you say again, you get this nice image, you can actually apply the image treatment technique and to recover the singularity of in the image. And if you have the singularity of the image, of course, you have the discontinuity of mu A, and you can also, through the singularity of the gradient of P, actually you can also recover the singularity of the diffusion coefficient, and many researchers consider this idea to recover mu A and dA in the second inversion. It's like an image problem. That was the idea in the paper of Netter and Scherzer in 2014, and also in the paper of Alberti and Amari, where they took the logarithmic function. If the U is the fluence of the laser, so it's always strictly positive, and take the logarithmic, you can separate the absorption from the fluence of the laser. So of course you don't know U, but you know that logarithmic of U is smooth and logarithmic of mu A is discontinuous. It's like you have this discontinuous plus smooth part, and people working on image treatment, they can separate the two functions very well. So the drawback of this approach is that you cannot recover the exact value of the absorption mu A and the diffusion dA, and these values are very important for a medical doctor to really decide if the tissue is in good health or not. So if you want to recover not the discontinuity but the exact value of mu A and dA, you need actually to perform the second inversion. And that lead me to talk about the penetration depth and the photoacoustic resolution depth, and why we have a very low depth resolution. And this is because, again, the property of the solution to the elliptic equation U, and because U actually far away from the illumination from the source of the laser is almost zero. It decays very fast inside the domain omega, and because U is a solution to an elliptic equation. And this is why we have very low resolution depth, because you multiply mu A by U. U is very small. So if you want to recover mu a from the product mu a u, it will be almost impossible. Just if you want to assume that you know the function u, you have the function u. If u is very small, then if you want to recover mu a, you need to divide by u. You divide by u, which if u is very small, then you have an amplification of the error coming from the modeling or from the numerical treatment of the problem. But still, we have a very nice, a very good depth resolution compared to imaging with a single wave. If you consider only, for example, imaging the absorption coefficient and the diffusion coefficient using only electromagnetic wave, we have, I mean, we have almost 10th the depth resolution of the photoacoustic imaging. So let me, develop this part in the rest of this talk. So in the rest of this talk, I will only consider what we call the second version, or the quantitative photoacoustic problem. So of course we had a lot of, many works about related to this imaging modality. You already had two nice talk about imaging, photoacoustic imaging. So the first work I want to talk about related to this quantitative photoacoustic imaging is a work that has been done with QRN, and we consider in this work the layered media. And why layered media? Because if you see the photoacoustic machine, imaging machine, and this is like a, ultrasound wave, just using this device, this acoustic device, this transducer, just made the hole inside this optical device, and they send the laser through the hole, and they measure at the same time the acoustic wave, the pressure on the boundary. So what they do in general, they send the wave, the electromagnetic wave from one side, from this side here of the rectangle, and they measure from the same side. And actually, we wanted to study the imaging depth of the resolution depth of the photoacoustic imaging, and we had this idea to consider layered media and say we want to study how far can we get in depth, with a good resolution. So we assume that all the coefficients are depends only on the variable y, the vertical variable, and we assume that the coefficients are periodic in the tangential variable x. And here, what is really which is very realistic is we measure, we send the wave, the electromagnetic wave from one side, and we measure the acoustic wave from only one side. So of course, if you consider this geometrical assumption, this is metric not trapping, for this inverse problem, you consider this assumption is not satisfied here. So here we will perform the global inversion, both inversion at the same time. Again, we assume that dA and mu a are depending on the variable y, and c, the speed, is depending only on the variable y. So this is the first equation, modeling the electromagnetic wave, the fluence of the laser U, and this is the acoustic wave. Again, we assume that all the solutions are periodic in the tangential variable. So I didn't make this remark, and why the first equation is time independent, and the second equation is time dependent. This is because because the big difference between the speed of the electromagnetic wave and the acoustic wave. So the electromagnetic wave is propagating much faster than the acoustic wave. This is why we consider here the model of the electromagnetic wave time independent. Actually, we take the mean over the lap of time where the electromagnetic wave is propagating inside the domain omega. Again, beta is here depends on the is a damping coefficient. It depends on the transducer and the contact between the transducer and the biological tissue, and it can be a function of x here. It should be a function of x, but here we consider it the constant to simplify the model. So we have the coupling between the two waves, and we measure the acoustic wave on the boundary for an interval of time t. And we have these result. This is stability result. So the stability result is an estimate that gives you how the determination of the coefficient mu a and dA depends on the error in measurement or model error on the boundary. So here we derive this weighted stability estimate, and you see if you have two measurement, two-time measurement, we call it is P and PE tilde, and here we need for each coefficient we need two measurement. Why? Because we have two functions to recover. And if you remember, the measurement will give you two internal measurement functions. So if you consider a degree of freedom related to the two functions that you want to recover, mu a and dA, so you need two measurement set on the boundary. So we consider two sources, P1 and P2, and we measure, we actually control the coefficient difference between the two coefficient, the coefficient mu a and mu a tilde and dA tilde by the difference between the measurement on the boundary for for t between 0 and capital T. And this is a very explicit stability estimate. Why? Because here we considered layered media. So basically the function are 1D. And we have, for 1D problem, we have less geometry, and we can control better the wave equation. So this is why we have a very nice stability estimate. So here you see the Hölder power is 1/4. This does not depend on the quality of the measurement of the solution. And the weight here is UM is explicit here, and UM is a function that is 1 at the top, that 1 is 1 here and 0 here, and decay exponentially from 1 to 0. Okay. What does it mean? It means that close to the top where you are making the measurement, and also where you are sending the electromagnetic wave, you have a very good recovery of the coefficient mu a and dA, because UM is almost 1. So we have a Hölder stability, classical Hölder stability estimate. But when you are far away from that region, UM will decrease exponentially, and the UM will be extremely small. Okay, you can take out the minimum of this function in that region, and you add it to this constant would blow exponentially in depth with respect to the variable depth. So this is the stability estimate that shows really that we have a very good resolution close to the boundary where you are taking the measurement, and very low resolution far away. Now we move to the general media, and this is a new work with Rick and Moraccioli. And here we wanted to somehow to extend the result that we obtained for layered media to general media. The idea is to consider a very realistic model. So we consider a Dirac function outside the domain omega. So this is the electromagnetic excitation, elimination. So we consider two Dirac functions situated at C1 and C2. So this is the equation satisfied by U1 and U2. And we assume that we know mu A times U in the whole of omega, okay? So we have two sources, two point sources at C1 and C2. We measure mu A times U1 and mu A times U2. And again, the inverse problem, if you have this function everywhere in omega, you want to recover dA and mu A, okay? So this is the inverse problem. So we because we have two green functions, so we actually proved that close to the Dirac point, the two solutions are the gradient of the two solutions are not linearly dependent. This means that we take the gradient of U2 over U1 in a ball centered at X star, with X star is close to X1 or X2. We prove that this is lower bound by eta, with eta is a constant that depends only on the parameter of the problem. And this is how we propagate the information into inside the domain omega. And we prove this result, this stability estimate. It's Hölder stability estimate. So you can think that you think that the stability is Hölder, so we have a beta recovery of the coefficient everywhere in omega. Actually, it's not the case, because we'll see that gamma can be very small. And it is similar somehow to the result obtained by Alessandrini and his co-author in 2015 under strong condition assumption on the boundary condition. And here, because we considered some more realistic model, I mean the excitation is from outside, we didn't have to assume something on the boundary condition. So let me explain you the result briefly, the proof of this result, this stability estimate. Let me just again explain the resolution depth and why the solution is exponentially decaying. So if you have this green function U, so again, just go back to this the equation of the. So here, if you assume that dA and mu A are constant, you get the green function with constant coefficient. Okay. And this is what we have here. We have it explicitly. So you can see that the solution is exponentially decaying with respect to the distance to the point sources. If x minus c goes to infinity, you can see that the solution U is decaying exponentially. This means that if you are far away from the source, the solution is extremely small. So this is well-known fact for a constant coefficient, elliptic coefficient. So we did it for the general coefficient, general function coefficient, assuming that dA is C11 and mu A is C01. So we derived this exponential decay of the solution, and we actually can distinguish between how the coefficient, how the function will decay exponentially with respect to the distance to the position of the sources. Okay, so let me briefly explain the idea of the proof. So the proof followed, the proof of Balan-Ullman in 2010. Considering two internal data, H1 and H2. The only difference is that here we don't assume that we don't have a critical point. So in that paper, they assume that they don't have any critical point inside the domain omega. So what are the critical points? The critical point are the point where the gradient of V vanishes. I will explain this later. So the idea is very simple. So you have two solutions. You have again these two functions mu a u1 mu a u2 everywhere in omega, and again you want to recover dA and mu a. So what you do first is you divide h2 by h1. H2 is mu a times u2, h1 is mu a times u1. If you divide h2 by h1, you get u2 and u2 over u1. And since you know h2 and h1, it's like you know the function v. And you see here, I mean, v satisfies these elliptic equation. Just play with the two elliptic equation satisfied by u1 and u2, you can derive this elliptic equation in omega. And you see here why we have, I mean, we have a nice recovery of the coefficient. Why we have Hölder stabilities, because we moved from an elliptic equation to a transport equation. So here you know v, you know the function v everywhere in omega. You want to recover sigma. So it's a static steady state transport equation. It's well-known steady state transport equation. Actually, we revisited this equation and we solved it numerically recently with Tao Yin. So so if the gradient of v, I mean, does not vanish. I mean, if gradient of v does not vanish and v is smooth enough, you can use the characteristic method to solve this equation. But the problem is the gradient of v can vanish, and you cannot use the characteristic method, and you need to find another way to solve the equation. So you need the regularization, other kind of method to solve this equation. So if you multiply, you integrate by part, and that was the idea in the paper of Alessandrini in '86, you will get this estimate, just integration by part. Okay, you get this estimate here, and you see you can control actually if you have two sigma and sigma tilde, and v tilde. And we're trying to derive stability estimate, so we have always two coefficient, two solution corresponding to dA mu a and dA tilde mu a tilde. Related to this stability estimate. Again, just remind you, you have dA mu a, dA tilde mu a tilde. And so each of these, the data will give you the coefficient sigma and sigma tilde, v and v tilde, and you have these two transport equation. And actually you can estimate the difference between sigma and sigma tilde this way. And you see that you have almost a stability, Hölder stability estimate. Actually, here on the right side, you will recover the difference between v and v tilde in H2 norm. Okay, but you can interpolate and you get this norm in A2 with this Hölder power. So assume that you know sigma on the boundary, so this will vanish. So this is almost a Hölder stability estimate. If the gradient of v does not vanish. Okay, if the gradient of v does not vanish, you just take the minimum outside and you recover a nice Hölder stability estimate. Okay, but in general, gradient of v can vanish, and to deal with, we need to use the unique continuation. So what is the idea? Since v is a solution to this elliptic equation, so gradient of v cannot vanish, assuming that the coefficients, of course, are smooth. Gradient of v cannot vanish on a small ball. Okay. And you can quantify that. This is a unique continuation. You can quantify how the gradient of v will vanish in a small ball of radius r. And in terms of r, okay, if you take r to 0, of course, this quantity will tend to 0, and you study how this quantity will tend to 0 with respect to r, and that was done by Grafalo and Lin. Many work related to this quantification based on the frequency function. So here, this is the how we can take out the gradient of v. We just take out the gradient with a small ball and play with the size of R in order to derive the stability estimate. So of course the C here is related to the multiplicity of the critical point or critical set of the gradient of V. If gradient of V will vanish at high order, C will be large, and gamma will be inversionally proportional to C, will be very small. Okay, now we get the stability on sigma minus sigma tilde. We through this unique continuation principle, we want to recover again. So sigma is dA times u1 power 2. So again, we want to recover dA and mu a here in this problem. So we just remark that 1 over u1 is actually the solution to this elliptic equation. So since sigma is recovered in this first step, we just use sigma to recover w, and w is exactly 1 over u1. And you can see in this problem, all the other parameters are known. So this is how we derive the stability estimate. And again, if C goes to infinity, it means that the gradient of V will vanish with higher multiplicity. This gamma will tend to 0, and we will have a very bad stability estimate. And this does not really reflect this result. I mean, we have in this result we have a very good stability estimate close to the boundary. And gamma, it seems that like is the average about, I mean, this is the maximum is 1 over maximum multiplicity over the whole domain omega. Okay, so if you look closely to these three steps, you see that this equation is local. It's almost local actually. You can solve it. I mean, you can integrate over the characteristic of the gradient of V, the speed, and you can actually avoid the critical point if you want, etc. But this is a local equation. Okay. Again, here, I mean, just to quantify the stability of the coefficient of the resolution of this transport equation. So this is a local equation. Now, if you want to recover the coefficient, you need to solve the problem of the whole omega, and this is not a local equation. You need to solve the equation, the whole of omega. So you need really to average over all the multiplicity of the critical point, and this is very bad. So if we want really to study the depth resolution, we need really to make it local, and to get rid of this step. And this is what we did here with Key 2. So this is a very recent work. So we obtained this stability estimate. Let me just explain the stability estimate, and then I will explain the proof, briefly the proof. So here again, we assume that the coefficients are known on the boundary omega, on the boundary of omega, gamma. And you see here this region theta r is the intersection between the ball of radius x naught and omega. Omega is the boundary of omega is this one here. You can see, and x naught is supposed to be the impact point of the laser wave. And we assume that the source is strong close by this point x naught. So this is why we want to study the stability estimate close to this region here. We expect to have better resolution close to this point x naught. So this is exactly what we proved. We proved that we have a stability, Hölder stability estimate with gamma of r. Gamma of r is the radius, is the distance to the point x naught in this region. Okay. And with gamma of r is the decreasing function of r. So gamma of r will tend to constant is 1 minus theta when r tends to 0. This means that we have a better resolution. We have a better resolution when we are close to these x naught this point X naught. So this is Hölder power with this constant, of course, is independent of R. So this is the stability estimate. So let me briefly explain you how we did to obtain this stability estimate. So here we don't actually, I said local, we can actually solve it algebraically. We just, and this is what happened in real life. People, they consider many, they take many measurements. So we have many HJ, and each measurement will give you a linear system. This is a transport equation where we just wrote it in terms, it's like a linear system on gradient of logarithmic of sigma. Sigma again is dA times U1 power 2. With M is something that you know, is something that is related to V, the gradient of V. M is exactly gradient of V2, the gradient of Vn plus 1. If you assume that locally this matrix is invertible, so we can recover gradient of logarithmic of sigma locally at the point where M is invertible, okay? So it's really local. So we can recover logarithmic of sigma everywhere where of course, this system is invertible. And we can assume that you have as many measurements as you want. It's very, actually, it's very easy to take many measurements in photoacoustic. Okay, so the crucial point here is, again, is to substitute this, this inversion here, this global inversion in omega, by this local inversion, okay? Here, of course, we assume that sigma is smooth. Actually, you can prove that the square root of dA, the diffusion coefficient of dA, of course, is smooth, satisfies this Cauchy problem. This Cauchy problem close to the boundary where you send your laser and where you are taking the measurement. Okay, so the idea is to propagate the information from the boundary. And using the fact that you know the recovered sigma close, in this region here. Yeah. So we recover sigma in this region. We don't have to recover sigma everywhere. We recover sigma just here, locally. And we want to propagate the information from the boundary using that sigma is known in that region. So we will solve this Cauchy problem. So if you think about solving Cauchy problem, think about Carleman estimate. So what we did, we just use Carleman estimate in ways, in the clever way, in order to obtain this stability estimate, the Hölder power that decrease when R goes to 0. So this is what we did. We used this method numerically, and we recovered the coefficient dA and mu A locally. We didn't have to solve the whole problem everywhere in the domain omega. We just make it local and then close to the measurement set, and we had a very good result. Now I move to the conclusion. Okay, almost done. So we derived a very nice Hölder stability estimate, pointwise stability estimate, that actually showed that the reconstruction of the optical coefficient is very stable, close to, to the optical elimination region sources, and it deteriorates exponentially far away. So this stability estimate is in agreement with the experimental observation. Now, what we want to do, in the future, is to study the attenuation. So if we go back to this first inversion, so in the first inversion, I talked about reversal time method and improved the version of reversal time method, etc. Assuming that the wave will propagate without any attenuation to the boundary. But in real life, you have some attenuation related to the also the absorption of the wave by the biological tissue. And I think Otmar gave a very nice talk about attenuation in time domain or frequency domain. Frequency domain, if you, so the kind of attenuation considered by Habib in this paper was the classical attenuation operator. You multiply just the coefficient by the first derivative of the solution of pressure wave. So in the frequency domain, that will give you a linear function of omega, but it will be local in space variable. So Otmar talked about no local attenuation operator in space variable. So what we want to do, and this is one of the research direction in our project, is to consider a no-local operator in frequency domain with respect to space variable and with respect to the frequency at the same time. We want also to study the two-photon absorption model proposed by Quirin recently. So as I said, the resolution in depth is low, actually. It's not very good. And one way to improve this resolution is to use this two-photon absorption model. And it will increase the intensity of the field, but it will make the linear equation nonlinear. So we have quadratic term to deal with. Another way to improve the resolution in depth is to use the nanoparticle and the resonance phenomena. So just send the nanoparticle, metallic nanoparticle inside the biological tissue, and you can actually heat the biological tissue from inside by playing with the resonance, electromagnetic resonance of these nanoparticles. So we had very nice work with Margot, 2018. So we want to improve these technique, and you can find all the work that they presented here on my webpage. Thank you very much for your attention, and I will be very pleased to answer your question if you have.
Thank you, Faouzi, for a great talk. And as you just said, the floor is open to questions. So please either signal yourself with raising your hand, or use the Q&A box or the chat box, and we'll unmute you so that you can ask your questions. Okay, so we have one already from, let me see, I can find out who is it, who raised its hand. Let me see. I can't figure out who eventually asked the question. No open questions yet. So actually, let me start with the questions, Faouzi, just to launch the debate. So in this thing about this, in the second inversion, essentially you use the quotient of the two measurements to transform the problem into a transport equation.
Yeah. So this is what is beautiful in this method. So you move from elliptic equation, you see the elliptic equation, to a transport equation. So this is how we gain in this inversion. Go back to this technique.
But that's supposing that you have very good control on the data, and in particular, so you say the data consists of the multiplication of a smooth function by the coefficients, and but if you have errors in your measurements, maybe the ratio of I think you call them H1 over H2 may not be as smooth as you expect.
Yeah.
So
yeah. So you are saying, I mean, if we have error, I mean, in the measurement, I mean, in H2 and H1. So if we have noise, so what happened to this transport equation? So this was your question.
Yes.
And you see that, I mean, this is a stability estimate that we get, I mean, so this transport equation. Again, so here we assume we are not solving transport equation. We assume that we have already a solution to this transport equation, because if you assume that sigma is any function, any positive function, any function, it will be hard to prove that there exists a solution to this transport equation. So here we assume that we have really a solution to this equation. So if you add, I mean, we say if you add noise to the measurement, this means that you add noise to V. That will, I mean, that will, first of all, you are not sure to have existence of solution to this equation. Okay.
Right.
But in stability terms, I mean, you can control the error, I mean, the measurement with this term. So we have V minus V tilde is like the error here. It's like error in the measurement. Assume that V tilde is V plus some error in the measurement. So you get the error term on the right side. So we can control sigma minus sigma tilde times gradient of V power 2 by that term, I mean the error term. Assume that it's epsilon. If the error is small, then this guy will be small. So again, if when the gradient of V does not vanish, you have a very good control of sigma. If gradient of V vanishes, then you will have some problems. And this is why if we average over all, I mean the multiplicity of the critical point, we end with a very bad stability estimate. I mean, this stability estimate gamma can be very small.
Mm. Thank you. There is a question by Paul Sachs. Paul, you're allowed to talk, so why don't you ask your question directly?
Hi, Eric. Hi, Faouzi. So I was just wondering about the beta in your original boundary condition. That maybe this relates to the absorption question. Does it ever make sense for that to be allowed to be complex?
Beta complex?
Yeah. In the application you're concerned with.
Let me see. You beta here?
Yeah, that big.
I think beta. I mean, in time domain, beta should be real, strictly positive constant. Yeah, but in the frequency domain, I mean, if you assume that beta is a function of x, if you frequency domain, you can have a complex function. Yeah, I agree. You can have complex function. But beta here again, this is beta is related to the, I mean, how the acoustic wave is refracted through the transducer when you put the transducer on the biological tissue. And that will, I mean, this is exactly the attenuation in this system. Otherwise, the wave will propagate, the energy will be conserved.
Right. Okay, thank you.
Thank you, Paul. There's a question by John Yang. Yes. John Yang, you can talk.
Okay. Yeah, thanks, Eric. Oh, thanks for the wonderful talk. So I have a question related to stability. Can we expect to have like a Lipschitz type of stability by including more data like multi-spectral type data in the setting?
Yeah. So I mean, this is what I mean. Lipschitz stability, it will be very nice, but I mean, it will be not very realistic because again, the solution is decaying exponentially inside the domain omega, because you are solving this elliptic equation. But though you have, I mean, assume that you have Lipschitz stability. In theory, you can have Lipschitz stability. Assume that you have Lipschitz stability. The constant, I mean, the constant can be very large. Okay, if you take the stability in the whole domain omega, the constant here actually is very important in the stability estimate. The constant here. So I mean, this stability will give you, I mean, how the algorithm will converge to the true solution. You construct your algorithm, and you want to have like an a priori estimate of the error, This constant will be, I mean, very important there, because if this constant is very important, then it will slow the convergence, not only the power gamma. But again, if you consider the stability estimate in the whole omega, you expect a very big constant, because this it's like you divide by u. This constant is almost 1 over u. I mean, if you assume that everything is nice elsewhere. I don't expect to have a very good stability estimate in the domain omega, the whole domain omega, but expect to have a very good stability close to an impact point, to the region where we are. We send the electromagnetic wave, where the solution U is important. Far away from this region, the solution decay exponentially will be very small, and that will generate some instability in the reconstruction of the coefficient. Yeah. I hope that I answered your question.
Yes. That's fine. Okay, very good. Thanks. Yeah.
Thanks.
Thank you, John. We have a question by Otmar. Otmar, you've been unmuted, and please, if you want to ask a question.
Hi, Faouzi. Nice to hear a talk from you again. It's a long time. So I was referring to your discussion which you made at the end, and I hope my microphone does not stop, because my phone beeps all the time that the accu is low. But so you were said you're using this this somehow internal sources to illuminate this stuff. So these nanoparticles.
Yeah.
Do you think they behave similar as if you excite the object with a laser? That they just also give an impulsed source, or that they just gloom all the time afterwards?
Yeah, that's a good question, because I don't expect to reach the resonance of all the nanoparticles at the same time. But actually, what we will do, actually, people do in general, they just move the frequency of the excitation, and for each frequency we reach some resonance of some. Of course, the resonance will be the resonance of the system nanoparticle plus the biological tissue, not only the nanoparticle. So this is, since you don't know the optical coefficient of the biological tissue, you cannot really decide which frequency you have to use. But if you move the frequency, then you will, for sure, you will generate some resonance inside these nanoparticles, and you expect to have a photoacoustic effect. I mean, you amplify the field around these nanoparticles, and through the photoacoustic effect, you can have some heat and generate some acoustic wave.
Okay.
But I don't expect that the signal. Again, here we because of the decaying of the solution in depth, I don't expect to have a very good resolution far away. But it can improve a little bit the depth resolution of the general method.
And it can be localized, probably.
Yeah, it is
not
localized.
in the whole. Mm-hmm.
Yeah. It is localized. Actually, what we proved, actually, you can recover the coefficient at this close. Nearby the nanoparticle. So in theory, you can do many things. You can derive some stability estimate, etc. So what expect in experimental setting? Experimental setting is just you play with the frequency, and you measure your wave, and you see the image that you're getting, and from this image you expect to have better resolution, because these nanoparticles are inside the domain omega. So it's like they play like internal sources inside the domain omega.
Mm. Thank you very much.
Thank you.
Thank you, Otmar. Are there any further questions? don't see any activity in the chat box or in the Q&A box. But anyway, thanks everybody for attending. Thank you, Faouzi, again for your talk. It was very interesting. And, I'm not saying that because I'm a little bit part of some of it, but it was very nice. See you all next week for another Imagine seminar. Next week, we're hosting Fioralba Sacconi from Rutgers. And thanks again, Faouzi, and have a great day, afternoon, or night, wherever you are in the world.
Thank you.
Bye-bye.
Bye-bye.